পার্টিসিপেন্ট তো ম্যাডাম অনেকেই আছে, কিন্তু এখনো মানে অত জয়েন করেনি আর কি, মানে করবে আর কি 10টার পর। আচ্ছা, হ্যাঁ আছে ওটা। এখন এখানে হলে তো ভালো হবে ম্যাডাম, কিন্তু
क्या हो रहा है?
আপনার নেটওয়ার্কটা কি স্লো আছে নাকি নেটটা? দুটাতেই তাই দেখে নেটওয়ার্ক এরর বলে। আচ্ছা, হ্যাঁ, দেখি অন্য কথা বলে দেখি কি হয়েছে। হ্যাঁ ঠিক আছে, আমি পার্টিসিপেন্ট এখন জয়েন করছে 5-6 জনের মতো জয়েন করছে 10টার থেকে তো। 100 জনের বেশি, কিন্তু 100 জনের বেশি আসে না আর কি। অ্যাকচুয়ালি ম্যাডাম এটাতে না আমাদের ইউটিউব স্ট্রিমিং হয় আর কি, এটা ইউটিউবে জায়গা বস্তুটা জিনিসটা আর কি, তার জন্য আর কি দেওয়া হয়েছে। তা দেখুন একবার ট্রাই করে আমি কথা বলতেছি। আচ্ছা, ঠিক আছে। হ্যাঁ হ্যাঁ হ্যাঁ, দেখতেছি ম্যাডাম। কথা বল। ও, ঠিক আছে, ঠিক আছে ম্যাডাম, দেখতেছি। हाँ सर, मेरे को बुला रहा था सर, ये मैडम का तो वहाँ पे लोड नहीं हो रहा है वो पेज, बोला कि सिर्फ उससे ही 3-4 बार ट्राई किया तो फेल हो रहा है, बोला बोला नहीं, मैं बोला नेट स्लो होगा, बोला नहीं नेट तो मुझे सब खोल रहा है, आ रहा है जा रहा है। वही बोला तो सब तो मेल भी आ रहा है। फिर वो कल वाला भी ट्राई किया, दोनों में ट्राई किया, मैं बोलता हूँ फिर से। हाँ हाँ हाँ। ম্যাডাম ওটাতে এখন মানে আপনাকে লিঙ্কটা পাঠাইছে না, ওটাতে ক্লিক করে দেখুন, ওখানে নাম আর মেল আইডিটা দিতে লাগে। অ্যাকচুয়ালি ম্যাডাম
Rajesh sir, I think madam has joined. Hello, Rajesh sir. Welcome, madam. Professor Vinda Bhaumik. I am Dr. Chitrakan Sahu from MNIT Jaipur. Ma'am, am I audible?
Hello? Hello?
Yes, yes, madam.
Can you hear?
Yes, I can hear you.
Okay. Hello?
Yes, yes, you are audible, madam.
Okay. I have
There
one.
is issue with some matter.
I have some network issues, so that is why what I will do, I will send all the PPT to you, and if you can please that control the PPT, and I will tell which PPT you have to go. Can you please anyone do for me? For otherwise, the problem is that I can't open WebEx from my laptop.
Okay, okay, okay. So, Rajesh sir, I think you can take
I am
your
sending my
presentation
PPT
and
to
you can.
Rajasthan. Okay.
Yeah, yeah.
Okay. Okay. Thank you.
Yes, दोनों साइड से
Yeah, yeah. Now you are presenter, sir. If any slide come, then you can share.
यस मैम यस सर मैडम का लैपटॉप में सम इशू है तो
Okay, okay. So, welcome participants. We are going to start in few minutes. Okay. So, our speaker is here, Professor Vinda Bhumik from MIT Silchar. So, he'll be sharing the presentation very soon. Then we'll start the lecture. So, please be connected.
है मैम आठ से पीपीटी হ্যাঁ গেছে গেছে একটু দাঁড়ান আমি হ্যাঁ হ্যাঁ আপনি নেক্সট নেক্সট করে দেন হ্যাঁ ঠিক আছে ম্যাডাম অসুবিধা নেই আপনি নেক্সট নেক্সট বললেই হবে ঠিক আছে আমি শেয়ার করে দেবো
Okay, are you ready? Hello?
Rajesh sir,
Hello?
Yes, ma'am.
please share the presentation.
Yeah,
Yes, sir. Wait for 2 minutes.
because if you start, then only I can proceed.
Yes, ma'am. Wait for 2 minutes.
Hello?
Yes, madam.
Okay. Have you started presentation? Presenting?
It will be visible to you. I think Rajesh sir is sharing the presentation.
He will do that. Yes.
No, no.
So all the participants are from which field? From
Ma'am, they are from various fields. Few of them are faculty also, few of them UG students like this one. Okay, good morning, all the participants. And today we have speaker Dr. Associate Professor, National Institute of Technology, Silchar, and Dr. Bindavumi completed her PhD from NIT Silchar, and her research to tunnel acuity, then field effect transistor, carbon nano, and ferroelectric tunnel FET, and like your advanced MOS devices. And published more than 85 journals in various reputed journals like ITRS, and he has attended two patent and many conferences. I welcome on behalf of the committee Dr. Binda Bhumi today's session on emerging application of tunnel optical sensors and energy harvesting. Welcome, Dr. Binda Bhumi. I think it is.
okay. Thank you, Dr. Rajesh Saha. Yeah,
Wait,
thank you.
wait, it is
It is
sharing.
visible.
Wait.
PPT. PPT, you just ask all the participants.
Yeah,
Yeah,
yes, it is visible. Now you
Yes,
can
yes.
make a full screen.
Okay. Now I want
Yes,
to
I'm-
thank Dr. Rajesh Saha and Bharat Chaudhary for inviting me for giving lecture in the workshop. So we'll start because time is short. Already it is 10:10. So I'll start my lecture on application of emerging TFET structures in biosensor, light sensor, and RF energy harvesting. So why we go for emerging TFET structure? Why we go for emerging structure? Why not we start with the MOSFET, CMOS technology only? Despite being the most popular and established semiconductor device for electronic application, MOSFET has several limitations when scales down. All of you know that different short channel effects are there, different limitations are there. So downscaling severely degrades the leakage current, fails to reduce subthreshold swing below 60 millivolt per decade, thermal limit This 60 millivolt per decade is nothing but the thermal limit at room temperature. So in order to mitigate these limitations in MOSFET, TFETs have emerged as one of the prominent alternatives for low power application. So our major concern is nothing but the cost, power, and packing density for our integrated circuit technology. Okay. So say we want less cost, low power, and high packing density. Packing density means more number of devices per we want to integrate in a single chip. So in order to get those, we require some emerging TFET structures. Okay, then go to the contents. Next
Madam,
slide.
I think slide is not in parallel with what you talk. So Rajesh sir, please follow madam so that you can.
Yeah.
The
Someone
slide.
should sit. Otherwise, it is not
Yeah.
possible.
Ma'am, you can say next so that Rajesh sir can
I have
change the
some
slide.
problems, so that is why I can't show the PPT because WebEx is not down. I cannot open WebEx from my laptop and desktop, but it can open only from my mobile
Rajesh
phone.
sir, are you here? Rajesh sir. Hello, Rajesh sir.
Okay, so all of you consider the outline. Outline is based on introduction to emerging device, then advantages of TFET technology, MOSFET versus TFET, band-to-band tunneling, various emerging structures, TFET structures, application of TFET as biosensor, application of TFET as light sensor, then TFET as RF energy harvester, and various rectifier topologies. So first, we will start with the emerging device. So what is an emerging device? A device, please go to the slide number 3. Slide number 3. Next slide. Okay. Introduction to emerging device. So already I told you why we go for emerging device, because we need emerging device in order to replace CMOS so that we can overcome the short channel effects. Okay. Some of the factors, reduction of subthreshold swing, which is not possible in MOSFET, that is possible in case of TFET. Because in TFET, the basic principle of operation depends on the band-to-band tunneling. Okay, so a device with steep subthreshold slope, high on current at reduced power supply, high on-off current ratio, and unidirectional conduction can be explored to reduce power losses. So all these factors are the advantages of TFET, which can give you a better option as a replacement of CMOS. Okay, so what are the advantages of TFET technology? TFET has emerged as a promising candidate to mitigate the supply scaling challenge. So why we want to mitigate the supply voltage scaling challenge? Because we know that as we reduce the supply voltage in case of CMOS technology, what you will find, our threshold voltage is also reducing. So with the reduction of threshold voltage, what we will get? We will get the off current increases. So that will lead to more static power dissipation. Therefore, that problem can be mitigated in case of TFET. And TFET works on the band-to-band tunneling carrier injection mechanism in a reversed biased gated PIN diode. The structure of TFET is similar to gated PIN diode, but only the intrinsic part is controlled by the gate. But the intrinsic part is not completely intrinsic. We are giving some doping to the intrinsic channel. Why we are giving doping? In order to reduce the resistance. Otherwise, if you keep it completely intrinsic, then resistance of the channel will be more, and due to that we may get very less current. Therefore, the structure is similar to PIN gated diode, but the intrinsic layer is not completely intrinsic, but we are giving slight doping to the intrinsic layer. And the control of operation is nothing but field control operation, because gate is responsible for creating the inversion layer and drain to source voltage is controlling the current. Okay, so it has three terminals. One is gate, one is, next slide, go to the next slide, slide number, next slide. So what is the structure of tunnel FET transistor? We'll see. Next. You went to the previous slide. Next. Next slide. Please go to the next slide. No, you have crossed two more slides. Slide number 5. Slide number 5. Yeah, this one. So tunnel field effect transistor, it is a gated reversed bias structure. So it works on interband tunneling. So what is that interband tunneling mainly based on? The interband tunneling is based on Zener tunneling. As all of you know that Zener tunneling is possible in case of highly doped devices. We need a very narrow depletion layer, and due to that, what will happen? The valence band of P side will be at higher level than the conduction band of the intrinsic level. Therefore, what will happen? Electrons can come from the valence band of the P side to the intrinsic layer and causes tunneling of electrons from valence band of P side to the conduction band of intrinsic layer. So this type of tunneling is known as Zener tunneling, which we have already studied, where we have studied in BTech level the avalanche breakdown and Zener breakdown. This phenomena is similar to the Zener breakdown. That is why the tunneling phenomena which occurs in tunnel FET is nothing but a Zener tunneling. Okay, and it can device can operate both in P channel and N channel modes depending on the selection of your drain and source. You can reverse source drain junctions, and you can consider here electrons can form inversion layer if we apply positive gate voltage. If we apply negative gate voltage, then holes can also form the inversion layer. So a TFET can operate either in P channel or in N channel modes. Okay, so now next slide, you see the energy band diagram of a TFET. Okay, go to the next slide. Next slide, you can see operation of a tunnel FET. Operation of a tunnel FET, all of you see here in the figure, the vertical axis shows the energy and horizontal axis shows the position. So at source, channel, drain are marked and tunneling direction is shown. Now how you have created the tunneling junction? You have created the tunneling junction by applying gate to source voltage and drain to source voltage. Now when the device in off state, your red color graph shows the device is on state when VGS is 1 point, gate to source voltage is 1.5 volt, and red color shows when gate to source voltage is 0 volt, means it is the off state. Now all of you can see the tunneling window is shown using the dotted line. The tunneling width is reduced when you are applying positive gate to source voltage, and like that electrons can tunnel from the valence band of the source to the conduction band of the channel. Okay, so like that your operation takes place. Means tunneling phenomena will occur at the source channel junction. Now how will you decide? Because you are giving source a very high doping concentration near about 10 to the power 20 per centimeter cube or 10 to the power 21 per centimeter cube you are giving to the source, so that your source channel junction can act as a tunnel junction. Okay, and you are giving drain, you are giving somewhat less doping, so that at the drain end you may not get any tunneling. because in order to reduce the ambipolar current, which I am coming later, ambipolar current, the doping of the drain should be kept lower than the source doping. Okay, because we want the operation only at the source channel junction. Okay, so next is all of you go to the next slide. So next slide shows the ITRS. So ITRS, all of you, the different MOSFETs are there, nanowire MOSFET. Or next slide, please go to the next slide. Then we have nanowire MOSFET ITRS data is shown. Here we can see tunnel FET, others are also there. We can see for tunnel FET has from the year 2013 to 2028 a projection has been made, and it is seen that for tunnel FET the black part shows the research required and the blue part shows the development underway. So the tunnel FET is still under research. Still we are studying different structures, because one disadvantage of tunnel FET is that even if it can overcome many short channel effects, but the tunnel FET, the current is basically due to the band-to-band tunneling. That is why the current which is measured at VGS is equal to 1 volt or sometimes at 1.2 volt, it is very less. So in order to improve the on current and another capacitance, that is the gate to drain capacitance of tunnel FET is found to be very high. So that gate to drain capacitance is needed to be reduced, because if in a common source configuration your gate to drain capacitance is acting as Miller capacitance. So these capacitance we want to reduce. Why? Because this capacitance will create lots of problem. It will reduce the switching speed of the device. Therefore, what we have to do? We have to do some more research on tunnel FET structures, that we should get the advantages of tunnel FET, that is we can reduce the short channel effects, but the on current as well as the gate to drain capacitance, those two factors should be according to the ITRS requirement. Okay, that is why tunnel FET is still under research. Now ITRS targets of on current, off currents are shown. Off current and saturated current, TFET is marked using the red color. So we can see the high performance is at the top and TFET off current is below that, and saturated current is also shown in the figure. Saturated current for TFET. Now for loss standby power, you can see now TFET. So till now TFET has not reached the group 3,5 material. If we use group 3,5 or germanium, then we get more on current as compared to TFET. So TFET is still in research, and in TFET also we can apply some group 3,5 material or germanium as source or germanium as channels, so that we can improve the on current of TFET, so that we can tunneling width. The tunneling width is a deciding factor. Then in the next slides I will show you how the current is dependent on the tunneling probability of the carriers at the source channel junction. Okay, next slide, please go to the next slide. So tunnel FET versus MOSFET operation. All of you know that MOSFET is basically working on the principle of thermionic emission. You can see the structure of MOSFET. MOSFET is a symmetric device because drain and source terminals you can interchange both for N mode operation. N plus source is also N plus and drain is also N plus. But in case of TFET, this is an asymmetric device. One side is P plus, another side if source is P plus, drain is N plus. Now, if you see the energy band diagram, electrons are overcoming the barrier from the source and they are coming to the channel. With the application of gate voltage, you are reducing the barrier. But in case of TFET, the operation is already discussed. It is just a band-to-band tunneling operation. Electrons are tunneling via the junction, source channel junction. And the condition is that the width of the tunnel width should be less, within less than 5 nanometer. Otherwise, there is no tunneling. Okay, so they like that you can get the tunneling. Unlike MOSFETs, next slide, please go to the next slide. Unlike MOSFETs, the gate-controlled tunneling window in TFETs is able to effectively filter the high. Please go to the next slide.
I think, madam, there is some issue with the register network also. So I am going to stop the share and share it again.
Okay.
Wait a minute. I'm presenting now. Is it visible now?
Yeah, visible.
Yeah, now you can continue.
Hello, ঠিক আছে না? Everything is okay. Okay, now you see what is unlike MOSFET, the gate-controlled tunneling window in TFETs is able to effectively filter the high-energy carriers in the energy bands, and hence leads to a sub 60 millivolt per decade steep slope at room temperature. In order to achieve the projected energy efficiency benefits, a desert tunneling current at the device on state, a high on-off current ratio, and an average steep SS over a few decades of current change are the key design factors for the TFET. So these are the basic design factors. Means you in order to desert tunneling current at the on state, high on-off current ratio, and a steep subthreshold swing. SS means the subthreshold swing. Now we can see the effect of high energy part. In this diagram, first figure shows the MOSFET and second figure shows a TFET. In TFETs, the high energy part of the source distribution is cut off by the band gap region. All of you can see the high energy is the high energy part in TFET. The figure B shows TFET band diagram. In TFET, the high energy part of the source distribution is cut off by the band gap region, and this is responsible for leading to sub 60 millivolt per decade subthreshold swing. And in this case, phonon assisted tunneling becomes important. Okay, phonon is nothing but which is responsible for oscillations of collective oscillations of several atoms. So phonon scattering, phonon assisted tunneling may take place in case of TFET also. So what is the requirement for band-to-band tunneling? For band-to-band tunneling, next slide, please go to the next slide. For band-to-band tunneling to occur, an electron in the valence band of semiconductor tunnels across the band gap to the conduction band without the assistance of traps. The band gap acts as the potential barrier that the particle tunnels across. An electron travels from the valence band to the conduction band without absorption or emission of photon in the direct tunneling process. So tunneling process may be two-way. One is a direct tunneling process, another is the indirect tunneling process. So in case of what we will find, in case of direct tunneling process, an electron can travel from the valence band to the conduction band without the absorption or emission of photon. A tunneling particle acquires a change in momentum by absorbing or emitting a phonon in case of indirect tunneling process. So the difference between a direct and indirect tunneling process is discussed here. So in indirect semiconductor, what we will find, next slide, if you go to the next slide, you will find in the indirect semiconductors whose gamma centered direct band gap is much greater than their indirect band gap. Therefore, tunneling will take place. Indirect tunneling is the main tunneling process. See, in case of indirect band gap semiconductor, all of you know the indirect band gap semiconductors whose gamma centered band gap. What is a gamma centered band gap? Gamma centered is nothing but the point where maximum of the valence band is, or maximum location of maximum energy of valence band is obtained at the gamma centered location for both light hole as well as for both the heavy holes. So this gamma centered band gap is found to be very much greater than the indirect band gap. Therefore, the indirect tunneling is the main tunneling process for these indirect band gap semiconductors. The direct tunneling process is negligible in indirect band gap materials like silicon because the transmission probability decreases rapidly with barrier height. The most probable tunneling path is the smallest barrier. Obviously, the most probable tunneling path where the barrier is the smallest. For direct tunneling, the requirement for conservation of perpendicular momentum causes an increase in the tunneling. A particle with some, next slide, please go to the next slide. A particle with some perpendicular momentum in the valence band must tunnel to state with the same perpendicular momentum in the conduction band, which results in a longer tunneling path. In indirect tunneling process, the phonon does impart or absorb a change in the momentum of the particle. So the difference between direct and indirect tunneling process is discussed here, because we have two types of semiconductor: direct semiconductor and indirect band gap semiconductor. So the electron phonon interaction of the indirect tunneling process decouples the perpendicular momentum of valence band and conduction band. Please go to the next slide. An electron in the valence band can tunnel to any state in the conduction band such that energy and perpendicular momentum are conserved. That is a requirement. When tunneling will takes place and how? So electron is tunneling from valence band to the conduction band, but the requirement is that energy and perpendicular momentum should be conserved. Now we can see next slide. All of you see. Please see the next slide. Full band structure of unstrained silicon is shown in the figure. The band structure of silicon is showing the direct and indirect tunneling. Okay, here you can see the gamma centered band gap. Okay, gamma centered band gap is shown here. Gamma is a direct tunneling, an indirect tunneling path is shown in the figure. Here you can see direct tunneling occurs and indirect tunneling is also occurring, where phonon provides the momentum. So direct tunneling, indirect tunneling is clear, I think, from the figure. Next. In case of TFET means the inversion layer will be of electron. Electron will form the inversion layer. That is an TFET. In case of an TFET, applying positive gate voltage, pushing the energy bands downward. Now, if we apply positive gate voltage, all of you know that whatever voltage you are applying in the energy band, they will act as negative effect. If we apply positive gate voltage, then the energy bands will be pushing downward in the channel, resulting in narrower energy barrier between source and channel. This allows electrons in the valence band of the source to tunnel through the barrier to the conduction band of the channel under the influence of positive drain with respect to the source voltage. Tunnel FETs attribute to a low subthreshold swing below 60 millivolt per decade and substantially low leakage of state current. It has low leakage current as well as subthreshold swing is below 60 millivolt. These two factors are very much sure, but as you know, it has low off state current as well as it has low on state current also. That is the disadvantage. So by controlling the band bending of the channel, please go to the next slide. By controlling the band bending of the channel region using the gate bias, it is possible to abruptly switch on and off the interband tunneling. The BTBT current depends on transmission probability. BTBT means band to band tunneling current depends on transmission probability of the interband tunneling barrier. So then we can see on transmission probability of the carrier from the source to the channel depends on what parameters. That is very important. Now, by controlling those parameters, what we can do? If we know the transmission probability, then if we know on what factor our transmission probability is depending, then by controlling those parameters, we can increase the transmission probability so that we can get more current. Okay, go to the next slide. The tunneling probability can be calculated using the Winzel-Kramer-Brillion approximation as given below. Now you can see the tunneling probability can be easily determined. How will you determine mathematically? I can give you an idea. The energy band diagram you can plot, and at the tunnel junction you can see the barriers. By barriers, now if you know the barrier, then what you can see? You can see the barriers are almost linearly plotted. So we can consider the potential function is varying with respect to x, with respect to the distance linearly. By considering the potential function and by considering the Schrodinger wave equation, we can get the tunneling probability. Okay, so after calculating where we will calculate the tunneling probability, we will apply some approximation that the potential function varies slowly with respect to the x. So that is Winzel-Kramer-Brillion approximation. If we approximate that, then it will find that the tunneling probability is dependent on exponential factor minus 4 lambda root twice m. M is the effective mass, Eg is the band gap, and divided by 3 cube into h cut. H cut is a reduced Planck constant, Eg plus delta phi. Now Eg is a band gap that is known to you, that is fixed. Once you choose a material, you cannot change the energy band gap, that is Eg. And effective mass of the material is also fixed. And lambda is the screening tunneling length. Okay. Now what factor you can modify? The delta phi. The delta phi is nothing but the energy range over which tunneling occurs. That delta phi can be controlled. So you can see if delta phi is very high, then your tunneling window is more. So next diagram, please go to the figure 8 of next slide. We will see that in the diagram, the screening length is marked on state and off state. Off state band diagram is shown by the dotted line, and on state is also shown. Now here you can see, here it is different. Here source is, here in this band diagram, the source is N type and channel is intrinsic and drain is P type. Therefore diagram is like that. Okay, now you see the delta phi. Delta phi is which region? delta phi is the difference of energy level between okay, so that difference delta phi is the deciding factor for your tunneling probability. That delta phi means delta phi shows the difference between the left hand side is your source is having conduction band, and channel is having your valence band. So that difference is delta phi. Now by controlling the delta phi, what you can do, we can control the tunneling probability. So delta phi can be easily controlled by modifying the materials used in the in your research work. You can use germanium, you can use SiGe, you can use indium arsenide, you can control the gate in some other way. So different options are there. Like that you can control delta phi. Okay, and EG, band gap, you can use some low band gap material also. Instead of silicon, you can use germanium, you can use any other material. So like that you can control the tunneling probability, so that you can get more tunneling probability, because your current, that on current is proportional to the tunneling probability which you are obtaining from the band to band tunneling expression. So band to band generation rate is next slide. Please go to the next slide. The band to band generation rate of TFET is also expressed as G B to B, where A B to B is a constant, E square Eg to the power half. E square is nothing but the electric field, and Eg is the energy band gap, and exponential function of negative sign. With the negative sign, A and capital A and B are the constants. And E is the electric field, and Eg is the energy band gap. So band to band generation rate also determined, if you want to calculate the current, the generation rate of the carriers are also very important. So we can see the band to band generation rate is nothing but they are depending on the electric field at the junction and the band gap of the materials. So electric fields means it shows that if we get high electric fields, then obviously the tunneling, the generation 6 volt per centimeter, which is very high. So that high electric field is also a factor which is responsible for more band to band current. Okay, then we have some disadvantage. Why you are going for disadvantage? Until and unless we know the disadvantage, then what is the research? Why research is required? Because TFET, the conventional structure, has some disadvantages. That is why we are going for more emerging structures, so that we can overcome those disadvantages and we can get all the electrical parameters according to the ITRS requirement. Okay, so what are the disadvantages? We can see on current is less compared to on current obtained for conventional MOSFET. So on current of TFET is less. High threshold voltage, and it has low I on off ratio. Why it is low on off ratio? Because on current is low, because on current is dependent on the tunneling probability, and current due to band to band tunneling is found to be lower as compared to the on current of MOSFET. And switching speed, that I told you earlier also, a switching speed of TFET is lesser than that of conventional MOSFET. Due to what? Due to increased Miller capacitance. Why Miller capacitance is increased? Because what is the Miller capacitance? Miller capacitance is a capacitance which is connected between the input and the output terminal. So what is that? Gate to drain capacitance. For common source, most of the case we are considering the common source configuration. So for common source configuration, we will find that the Miller capacitance is very much increased in case of TFET. Why? Because your most of the capacitance is expressed as, all of you know, it is capacitance is expressed as Q by voltage, Q by V. So here, if there is the tunnel junction, the source channel junction is acting as a tunnel barrier. So most of the voltages are dropped in the source to channel junction, and very less amount of voltage is dropped in the drain channel junction, and therefore the gate to drain capacitance is found to be very much higher as compared to your gate to source capacitance. So that is responsible for your reduction in switching speed of TFET. So our aim, what is our aim? Our requirement is that we want to improve the on current and we want to reduce the gate to drain capacitances such that other factors, subthreshold swing, off current, should not be degraded. And many other factors are also there. Noise is also there. RF parameters are also there. So all the factors we should modify so that we can replace our in future we can replace the CMOS by the TFET. Okay, so next is various TFET device structures. Please go to the next slide. So next I will discuss about various TFET structures. Okay, so first structure, please go to the next slide. First structure is your lateral and vertical tunnel FET structures. So lateral tunnel FET, actually here the tunneling takes place along the direction parallel to the interface of gate oxide and the substrate, or at the parallel to the interface of gate oxide or channel also you can say. So here you see in the figure, it is written red color. Some arrows are given using red color and some arrows are given using blue color. So red color arrow shows the electron tunneling and blue color arrow shows the electron drift diffusion, because once tunneling will takes place, then electrons are attracted towards the drain through the drift mechanism. Okay, and here in the second figure, first one is the lateral tunnel FET, and second where the tunneling takes place along a direction parallel to the interface of gate oxide and channel. That is okay. The next is the vertical tunnel FET. So in case of vertical tunnel FET, what we will find? See the structure is different. In the above A structure, P plus is the source, N is the drain, and middle one is the channel. But in case of vertical tunnel FET, source is the P plus. P plus source is just below your channel, and channel and drain are just combined together. Drain is on the right side and in between channel is there. So tunneling takes place along the direction which is perpendicular to the interface of gate oxide and substrate. That is why it is vertical tunneling. You can say that vertical tunneling takes place. So red marked line, red colored arrow are showing the vertical tunneling, and blue marked arrows are showing the drift diffusion mechanism through which the electrons are flowing. Okay, so we can see in case of vertical tunnel FET, actually there are two types of in some of the FETs nowadays available, where advantage of lateral tunneling as well as vertical tunneling, both we can introduce together. Okay, so this is the first structure, modified structure. There are several structures. In my PPT I have included few structures. Next one is a 2D. Please go to the next slide. Next one is the 2D heterogate SY TFET structures. Okay, in case of the structure, you can see here barium oxide is given, SY structure, silicon uninsulated structure. In barium oxide is there, above the barium oxide you have P plus source, then channel and drain. You can see raised barium oxide structure. Here in the drain side, the barium oxide, one part of the barium oxide has been raised. Why? What is the advantage? You can see now you see the figure 10b, transfer characteristics are plotted. Transfer characteristic, which for transfer characteristic, when the raised barium oxide is present in the drain, in that condition that transfer characteristic is good, because I-on-off ratio will be better. So why the raised barium oxide is given in the drain region? The reason is written. The surface roughness scattering in the source and the channel raised barium oxide structure increases as compared with the drain region. This is due to the fact that peak electron concentration is located at some distance from the raised baried oxide in the drain, and accordingly peak electron concentration occurs at the source tunneling junction. Now where you will get the peak electron concentration, because tunneling junction is your source channel junction, at that junction you will get the peak electron concentration. Now whenever you increase, if you increase the baried oxide in the source region, then there is more scattering effect, because peak electron concentration is near to that level, that oxide, that region. Now if you increase baried oxide in the channel region, then also you will find there is some problem due to surface scattering. But if you raise the baried oxide in the drain region, then only you will find that the structure is better, because the peak electron concentrations are far away from that part. So even if you reduce the thickness, the peak electron concentration is not affected, and you can reduce the ambipolar current by increasing the baried oxide thickness in the drain region. So the overall channel mobility is also not degraded. You can get better I-on-off ratios in the raised baried oxide structure, but raised baried oxide only in the drain region. Okay, this is another structure. This structure is published in Electronics Letters. Then I have energy band bending showing at the tunnel junction. Now you can see the effect of high K gate dielectric. So all of you know, we are nowadays we are replacing the I am telling in short, because I have to cover many things. In one lecture it is very difficult to cover many things. So I am just telling why you are using high K gate dielectric, because in the last figure I have used high K gate dielectric. So what is the advantage of high K gate dielectric? In case of low K gate dielectric, if you reduce the oxide thickness below 2 nanometer, then there is huge amount of gate leakage current. Means gate leakage current due to tunneling. So that leakage current we want to reduce. So that reduction is possible only when you replace the the low K, that is SiO2, silicon dioxide, by some high K gate dielectrics. So one of the best example of high K gate dielectric is hafnium oxide, HFO2, which has the relative permittivity of near about 25. Sometimes it is it varies according to fabrication. Sometimes it is 22 also, 22 to 25. Its value is varying. So if we use it, then what we can do? We can increase the capacitance also, because epsilon is higher. Then the oxide capacitance is also more, and we can increase the thickness also. Then we can reduce the gate leakage current. So here in the figure, the tunneling barrier width with respect to the figure 11, all of you see the figure 11. Here vertical axis shows the tunneling barrier width and horizontal axis shows the gate voltage. Now if we use, you can see the dotted lines, the blue colored lines shows the high K gate dielectric only TFET. If we use only high K gate dielectric as a gate oxide, and the green color shows HG TFET. HG means hetero gate TFET. Now we can replace SiO2 by only high K gate, or we can keep a part of high K dielectric near the source junction and a part of low K gate dielectric near the drain junction. Now question is why? Why you are doing like that? We are doing like that because if we use high K gate dielectric near the source region, it will increase the current, on current, because it is near the tunneling junction. Now at the drain side, tunneling is responsible for your ambipolarity. Ambipolarity means the current which you get due to the application of negative voltage. Just last slide you can see, they're just beyond 0 volt, minus just point VGS when gate to source voltage is near about minus 0.1 volt. Then also you may get very high amount of current. So that current which is due to the opposite type of carrier is your ambipolar current. So you want to reduce that ambipolar current. So that reduction is possible only when if we place low K gate dielectric near the drain and high K gate dielectric near the source. So here also you can see the tunneling barrier width is reduced for you. If we use HG TFET, means high HG means heterogate TFET. Hetero means mixture of high K as well as low K. You are placing low K near the drain junction and you are placing high K near the source junction. So you are getting the tunneling barrier width which is lesser for HG TFET. Obviously, it is an advantage. So we can go for heterojunction or heterogate TFET structures, which is also another gate engineering. Means why we are doing this? Because if we reduce the tunnel barrier width, then we can increase the tunneling probability, and that increased tunneling probability will give you increased on current. Okay, please go to the next slide. Next slide is your heterojunction structure. Please go to the next slide. In heterojunction, because I told you, in order to improve the electrical parameters of TFET, we are using different types of structures. So in this structure, what modification is done? In this structure, sources consist of P plus silicon, and you see the channel is silicon, P type, and drain is N type. But at the tunnel junction, one silicon germanium layer is used. Why the silicon germanium layer is used? Because all of you know, silicon germanium, we can modulate the energy band gap of silicon germanium. By what? By controlling its mole fraction. Now, if we control the mole fraction of germanium from, we can vary the mole fraction of germanium from 0 to 1. Then what will happen? Means germanium is 0.1, germanium may be 0.2. Accordingly, silicon is also vary. So silicon germanium contents we can vary. By controlling the mole fraction, we can control the energy band gap, because in case of silicon germanium, the energy band gap is a function of what? It is a function of the mole fraction. So we can vary the energy band gap, and by varying the energy band gap, by varying the tunneling width, we can vary the tunneling probability, so that the on current of TFET can be enhanced by considering SIG at the tunnel junction. Okay, width of the SIG also you can simulate. After simulation, you can fabricate it. Simulation, why we are doing simulation? Because in order to get a better result, if you know the better result, then we can go for experiment or fabrication. Okay, next is effect of germanium mole fraction. Please go to the next slide. In this slide, the effect of germanium mole fraction on current is shown. Here we see with the increase on current is more for 0.3 mole fraction. Why? Because at this point your band bending is more, your tunneling probability is more. That is why near about 0.3 germanium mole fraction you are getting the more current. Okay. So okay, next is your energy band diagram. Now energy band diagram, I am not going in detail. The energy band diagram of you can see for electron quasi Fermi levels, EQFL means electron quasi Fermi levels are shown, and you have various conduction band levels. VGS at VGS 0.2 volt and VDS 0.7 volt. The graph is plotted, and it is showing how your band bending at the tunnel junction. The length from source to drain, the x-axis, the horizontal axis shows the length from source to drain, and you can see how the distance, how the tunnel barrier is reducing, and tunnel width is varying with the application of various mole fractions. That graph is shown because how the energy band diagram is also varying with respect to the mole fraction of germanium. Next is our go to the next slide. Next is a PNPR TFET. It is another TFET where you can use, you can see below the metal gate, we are using dual. What is the question? Whether anyone has asked any question? Hello?
No, ma'am.
If you have any question, you can ask at the end. Okay? Or you can ask now also. Any question is there? I think something is written, some chat box. I have not seen
no question,
it. Hello?
No question.
A tunneling junction is formed between the P plus region and a fully depleted narrow layer, N layer. Here the concept is that here also we are using heterogate TFET structure. You see, HFO2 high K gate dielectric is used above the source channel junction, and low K gate dielectric is used in the above the channel drain junction. Now here the in PNP TFET one N pocket is used, which is fully depleted, and that pocket is responsible for creating high electric field, and this pocket width you can modulate and you can shift and you can check whether you are getting the subthreshold swing, steep subthreshold slope you will get in the transfer characteristic, and it will provide you high on current compared to the conventional structure. Okay, next slide is a circular gate TFET structure. Please go to the next slide. Next slide is a circular gate TFET structure. In circular gate, what you will find? The circular gate, you see, the gate oxide is in circular shape, and at the tunnel junction, the thickness is lesser. Now, why we have kept the less thickness at the tunnel junction? So that the gate can easily control the tunnel junction. And a tunnel junction for BTBT has less dielectric thickness. The gate drain proximity is a cause of ambipolar current in TFET. So this structure can also be further modified. We can take the right hand side. If you control the radius, now what you can see, the gate oxide is of circular in nature. If we control the thickness, if we reduce the radius of that circle, all of you can see the circle is marked. If you can shift the center to the left hand side, and if you reduce the radius of the circle, then what will happen? Then the gate can be moved only towards the source side, and gate drain or underlap will be created. So gate drain underlap structure may be also a research opportunity for you. If you can create in this structure a gate and drain underlap, then this will cause more on current and it will reduce the off current, because gate drain proximity is a cause of ambipolar current in TFETs. Okay, so that is why this is also a research opportunity. You can reduce the ambipolar current, you can reduce the off current, but you can increase the on current. So what is ambipolarity? When a negative voltage is applied to the gate, BTBT current can also flow, which is defined as ambipolar current or ambipolar state. The difference between on state and ambipolar state is a position where BTBT occurs. BTBT means what? Band-to-band tunneling. In AM state, means an ambipolar state, unwanted BTBT occurs between channel and drain. The ambipolar behavior means that the tunnel FET is turned on even when it is expected to be turned off by applying negative gate voltage, which limits the feasibility and applicability of TFETs. Because if there is a slight increase negative voltage, if you want to operate the TFET in N TFET, then you are giving positive gate to source voltage. But even if you apply slight negative voltage, then you are getting high current. So this operation is unwanted. So that unwanted operation we want to reduce, because it will limit the feasibility and applicability of TFETs. Next is the IDVG characteristics. IDVG characteristic of the CG TFET. CG means the circular gate TFET, and HJ TFET means heterojunction. Heterojunction and heterogate, do not confuse. Heterojunction means silicon germanium is used in the channel and source is silicon. So you are forming a junction between silicon and silicon germanium. So that is a heterojunction. And heterogate means you are using high K gate dielectric over the source channel junction and low K gate dielectric over the gate over the drain channel junction. That is heterogate and heterojunction. Obviously difference is there. So always because one is a channel engineering, heterojunction is a channel engineering, or heterogate is a gate engineering, in order to improve the electrical characteristics of TFET. Okay, using gate drain underlap that I told you now, you can give some underlap to your structure so that your gate is away from the drain channel junction. It is shifted towards the left hand side. Then what will happen? Using the gate drain underlap. Now you see here in the figure, the underlap lengths are given. When underlapping is 0 nanometer, 4 nanometer, 8 nanometer, using gate drain underlap reduces the unwanted drain current, which is detrimental to circuit applications of the devices. So with the gate drain underlap of 0 nanometer possess the highest ambipolar current. Now you see at ambipolar current is measured at VGS is equal to -2 volt, and we are getting very high amount of ambipolar current when we are using no gate drain over underlap, means 0 nanometer. But when you increase the gate drain underlap, we are getting that our ambipolar current is reduced. So this is another research prospect for us. So next slide, please go to the next slide. That is gate, another structure of TFET. That is a gate on source oblique channel TFET. Now you see here gate drain underlap is given. The gate is shifted towards the left hand side. The gate completely covers the source channel junction. A part of the source and the complete and half, more than half of the channel is covered by the gate. Why it is like that? Because you have created an underlap of 15 nanometer. This underlap will provide you reduction of ambipolar current, better ion-off ratio, means you can control better your tunnel junction. Your tunnel junction you can control better now if your gate is completely covering the tunnel junction. So better ion-off ratio can be achieved by considering these structures. This structure is published in that paper. It is published in Superlatives and Microstructure journal. And this structure, next, go to the next slide. Next slide is germanium source vertical TFET. Please go to the next slide. That is germanium source vertical TFET. This structure is published in IEEE Transactions in 2019. So the germanium source vertical TFET structure you can see in this IEEE transaction on electron devices. So here you see that I told you vertical TFET, here P plus source is completely below the intrinsic silicon, that is the channel, and SiO2, the lower part SiO2 is showing the buried oxide, and drain is very thin, N plus. Now here which direction your tunneling will takes place? Tunneling will takes place from the P plus source to the silicon, blue color, yellow color to blue color. Yellow color is showing the P plus source and blue color is showing you the silicon. So tunneling will take place in the vertical direction, which is vertical to the interface of oxide and substrate. That is why it is vertical tunneling, as well as some vertical tunneling. And this vertical tunneling will provide you very high, very steep IDVG characteristic. That is why you are getting very less value of sub-threshold swing, and your device can operate as a very good switching application also. On-off state current ratio is also very good. So by increasing LUC, you can see LUC is marked. What is LUC? LUC is undercut length. This LUC also you can modulate, and you can find what is the effect of LUC on the device current, on the capacitances. Everything can be modified, and every parameter we can get according to our ITRS requirement. So germanium source, and source is consisting of a germanium material. Why germanium? Because germanium is having lower band gap as compared to silicon, and it will provide more tunneling, because we have seen in the tunneling probability expression the band gap is also a factor. So we can control the band gap, means we can reduce the we can use a low band gap material so that we can improve the tunneling probability. Here you can see next slide, on-off current ratio. So on-off current ratio is also seen here. Silicon thickness, The horizontal axis is your silicon thickness, and vertically current and ion of current ratio are shown. So we can see accordingly on current is improving and off current is why on current is improving? Because on current is improving in this structure as the thickness of the channel is decreased. The electrostatic gate control over the channel is immensely increased. In addition, as the electric field of the gate is parallel to the tunneling direction, since the source region in the figure, the last figure, the source region is directly underneath the channel. So reduction in the channel thickness results in a smaller total tunneling distance. That is why, since the last figure, vertical TFET, what we have seen, the reduction in channel thickness results in a smaller tunneling distance, and which offers huge current increase. Therefore, you can see the channel thickness, whenever it is reducing, the current is very higher. 3 nanometer current is very higher compared to 6 nanometer. Okay, please go to the next slide. That is optically gated TFET structure. We have some optically gated TFET structures also. In the TFET structure, you see what is the structure. Here, source, all of you see the figure 21. In optically gated structure, we have the source. We have in the source, we have used a germanium pocket. Then channel, drain, and gate is consisting of what? The gate is consisting of N plus silicon gate, where the incident photons are falling, and this TFET can act as optically gated tunnel FET structure. That later I will show you now. Next, you can see this optical generation in the gate region causes. Please go to the next slide. Go to the next slide. This optical generation in the gate region causes the excess electron hole pair generation. Those electrons having energy greater than the band gap of silicon will move from the valence band to the conduction band of the gate region, leading to the phenomena of photogeneration. The movement of these photo-generated carriers inside the gate are controlled by the applied VGS. So that is why it is a photo-generated structure where you can get optically gated TFET structure. This structure can be used as a light sensor application. Okay, that I will show you. Now next is, go to the next slide. Next is, till now I have discussed what are the structures and what are the advantages we can get and what are the research prospects, because till now research is going on. Now in this, from this slide onward, I will discuss about the application of TFET as biosensor. So biosensor is a very good application of TFET. So what we can see, what is a biosensor? A sensor converts physical quantity into a signal which can be read by an observer or by an instrument. That is the sensor. So what is a biosensor? A sensor that integrates a biological element with a psychochemical transducer to produce an electronic signal proportional to a single analyte, which is then conveyed to a detector. So it is nothing but which integrates a biological element with a transducer and to produce an electronic signal proportional to a single analyte. So figure is shown. Analytes are shown, sample handling and preparation, detection, signal and analysis, and response is also shown. So what are analytes? Analytes are target biomolecules, which are nothing but protein, toxin, peptide, vitamin, sugar, metal ion, pathogen and pesticides, etc. Okay. So what is the basic principle of biosensor? The basic principle is shown: analyte, then receptor, then molecular recognition, then transducer, then from the transducer you can measure it, after measurement you can record data and you can display it. Next slide, please go to the next slide. So this is the basic principle of biosensor. So biosensor is nowadays is used there are two types of biosensing application in case of TFET. One is the dielectric modulation and another is the gate modulated application. So in gate modulated, what we are doing, we are using here gate modulated structures are nowadays not used because it is very difficult to get gate modulated structure. That is why we are using dielectric modulated case. Dielectric modulated case means we are removing a part of the gate oxide and we are placing the biomolecules there, and we can use that TFET device as a biosensor. So the gate modulation, then we can easily simulate it also. Why? How we can simulate? Because we know the dielectric constant of those biomolecules and we can calculate the mathematical expression also, and we can simulate also very easily. Therefore, gate dielectric modulation technique is widely used when you consider the simulation of the biosensor TFETs. Okay, so this is the basic principle. Basic principle is clear to you, I think. Then is uses of biosensor. Why the biosensors are used? Next slide. The uses are clinical diagnostics, food and agriculture process, environmental, air, soil, water monitoring, detection of warfare agents, anthrax, crime detection. The various applications are there. So applications of FET as biosensors and innovative research prospects in terms of design, parametric studies, and analytical modeling. FET biosensor, next slide, please go to the next slide. FET-based biosensors are gaining interests due to their compact sizes, prevalent manufacturing processes, label-free detection. That is a more major advantage. That is why we are not using gating effects, because gating effect, whenever we replace the gate by the biomolecules, then label-free detection is not possible. That is why dielectric modulation technique is the most favorable technique out of the two, and established physics-based explanations. However, the need for miniaturization of transistors has led to the emergence of novel devices that can withstand the degradable effects of downscaling. One such novel device is TFET, which, unlike MOSFET, operate on the principle of BTBT and therefore offers low leakage current and better subthreshold swings. That is known to us. So current research is going on. If you go next slide, if you go to the next slide, please, I'm requesting to go to the next slide. So here we have written, E. proposed a dielectric modulated FET-based biosensor after the ion-sensitive FETs proposed in 1970s. So these, and Sarkar and Banerjee also presented an nanovac effect in demonstrating gating effect for positively charged biomolecules. And Key Meteor reported in partially filled nanogaps in practical cases due to static hindrance. That factor is very important. I am coming to that, static hindrance, and proposed a parameter, fill factor, defined as the percentage of the nanogap occupied by the biomolecules. So in the simulation case, what we have to do? We have to consider the cases of static hindrance. We have to do cases of fill factor, because whole part of the gate dielectric is not completely filled by the biomolecules. So the fill factor is an important factor while considering the simulation of the biosensors. Next slide. Next slide. Working principle. Please, working principle. What are the working principles? You can see working principle of label-free dielectric modulated TFET biosensor. That is very important. How it works. A portion of the gate dielectric material is etched out to form a nanogap. How we are forming a nanogap? We are etching out a part of the dielectric material. When biomolecules are immobilized in the nanogap, the dielectric constant of the gap changes. A change is reflected in the drain current and gives better sensitivity. A shift in threshold voltage is also observed. Now, from which equation you can explain this? Because we know that the gate voltage, gate to source voltage is equal to what? Is equal to the flat band voltage plus the surface potential minus Q into N bio by C oxide capacitance. Now the biomolecules are coming into the equation of potential balance equation of the device, of the TFET device. Now in order to, if you have if you put biomolecules of negatively charged, you can put biomolecules of positive charge, and you can change the dielectric constant of your gate by the corresponding biomolecules, then you can get a change in the surface potential of the graph. Now if you change the surface potential of your device, then what you will get? If there is an increase in the surface potential, there is an increase in the drain current. If there is a reduction in the surface potential, then there is reduction in the drain current. So by controlling the biomolecules and their dielectric constants, we can control the surface potential, and by controlling the surface potential, we can control the current, and then current is responsible is coming in the sensitivity measurement. So this action is carried out in the simulation process by considering an insulator having same dielectric constant as the biomolecule. Various types of proteins have unique dielectric constants, such as streptavidin, whose value is K epsilon, or sometimes some are writing K or some are writing epsilon. 2.1 charged amino acids like lysine, arginine, then glutamine and aspartate. ASP means aspartate. They have the dielectric constants varies from 11 to 25.6, and I have gluten, keratin and zein, where dielectric constants are varies from K is equal to 5 to 10. So these values of K are very important, because while you do the simulation, you have to consider that you have to replace your gate by those values of K, by those values of dielectric constants. Next slide. That the biosensor application is done in considering the circular gate TFET. That structure already I have shown you, and heterojunction TFET based biosensor. So in these structures, nano gap is created, and in the nano gap, biomolecules are entered. So dielectric modulated biosensors are shown for CG TFET and for HJ, that is a heterojunction TFET. And sensitivity, I already told you, current you can vary. How will you vary the current? If you vary the surface potential by varying the charged biomolecules or uncharged biomolecules also, then your sensitivity will vary because your drain current is varying. What are the sensitivity parameter? The sensitivity parameter is nothing but IDK by IDAR. So what is IDK? IDK and IDAR are the drain currents of the fat when nano gap is filled with biomolecules and with air. For air, if you replace it by air, then what you will write? You will write the dielectric constant as 1, respectively, at fixed gate and drain voltages. So this biosensor is published in IEEE Sensor Journal. This is my paper, 2019. So this is a widely can be widely used, but till now fabrication has not been done. Okay, so impact of negative and positive charge biomolecules on sensitivity. Next slide, please go to the next slide. Please go to the next slide. Next slide. Impact of negative sensitivity analysis is shown. The impact of negative and positively charged biomolecules is shown in the figure. The first figure is for A, B, we can see figure 24. Figure 24, A and B shows the sensitivity of TFET for first one. A is showing for A is for circular gate TFET and B is for heterojunction TFET. Now what we can see, with the increase of K value, with the increase of dielectric constant, our sensitivity increases. Why sensitivity increases? Because if we increase the dielectric constant, then my capacitance is increasing. Now if capacitance is increasing, then what will happen? The factor minus Q N bio means charge due to biosensor by oxide capacitance. If oxide capacitance is increasing, the negative factor, which is due to the biosensor charge biomolecules, is increasing. If negative minus Q by Cox, if oxide capacitance is increasing, then whole factor is reducing. And with if whole factor is reducing, then in order to keep constant the gate voltage, my surface potential is increasing, and due to the increase of surface potential, the sensitivity is also increasing because the drain current is increasing. The explanation is just simply from the potential balance equation of the TFET device. Okay, so C and D are showing the drain current, corresponding drain current for the circular gate TFET and HJ TFET. Now we can see figure 25. In figure 24, negatively charged impact of negative charge biomolecules are shown in the figure, and in figure 25, the impact of positive charge biomolecules are shown. Figure A is showing for circular gate TFET, and figure B is showing for the heterojunction TFET. And figure C and D are for drain current in transfer characteristics for the circular gate and the heterojunction gate TFET, heterojunction TFET structures. So what we have seen, with the increase of K, my sensitivity increases, but the increase of sensitivity is found to be more. The increase of sensitivity is found to be more for the positively charged biomolecules. Why? Because positively charged biomolecules deplete p-type channel and causes more tunneling of electrons, and hence sensitivity increases. Okay, so sensitivity both the cases increasing, but increase in case of positively charged biomolecule is more. Okay, so that is your impact of sensitivity. This is the sensitivity analysis. Next is comparison with MOSFET as biosensor. So we can see the comparison. Sensitivity of next slide. Please go to the next slide. Comparison of sensitivity of circular gate CJ. CJ means circular gate TFET. HJ means heterojunction TFET, and MOSFET biosensors for dielectric constant K is equal to 5, 7, 10, 12 at gate voltage 1.2 volt, drain voltage 1 volt for negatively charged biomolecule and positively charged biomolecule is shown. So what we have seen from the figure, one is for negatively charged biomolecule, first figure, and second figure is for positively charged biomolecule. So what we can see, sensitivity for circular gate TFET is found to be highest for all the types. So obviously it is a good prospect. So circular gate TFET structure already, it is already a mathematical model has also been established. Mathematically current model we have also established in IEEE transaction and IEEE transaction on device that is published. Now its sensing application is also good. Therefore we can easily use the circular gate TFET as a biosensor. Okay, next, yes, please go to the next slide and press 1 enter, then figures will come. Non-uniform hybridization. So that is the very important factor. These are the practical cases we have incorporated in our simulation. So non-uniform hybridization is what? One is a steric hindrance. Practically, the fully filled nanogap is rarely encountered. After the hybridization of biomolecules initiates within the nanogap and continues for a period of time, the already hybridized biomolecules hampers the entry of more biomolecules. So this effect is known as steric hindrance, and the effect of steric hindrance results in non-uniform hybridization of varying profiles of occupancy along the length of the nanogap. Because of that, different cases has been considered because of steric hindrance. So what are the cases we have considered? See the figure 27. In figure 27, A, B, C, D are marked. What is A, B, C, D showing? Profiles of partially filled nanogap. One profile is showing decreasing, B is showing increasing, and C is showing concave, and B is showing convex pattern. Comparison of sensitivities of step profiles of partially filled nano gaps in circular gate TFET, fill factors. You see the fill factors are considered. For figure ABCD is only showing how the nano gaps are partially filling. Means they are filling using the profile. One is decreasing, increasing, concave, convex shape. And figure E and F shows for CG TFET and HJ TFET when the fill factor is 32% and all the 4 cases ABCD are considered for different dielectric constant of the nano gaps. Nano gaps when they are replacing by your biomolecules. Okay, figure E and F and figure G and H are showing the fill factor of 58%. For circular gate TFET, figure G is for circular gate TFET and figure H is for heterojunction TFET. For the 4 different structures, decreasing, increasing, concave, convex. Now what we have seen, the sensitivity is found to be more for the decreasing structure. Okay, so these comparisons why we have made, because we have considered the practical case that whenever after the hybridization of biomolecules initiates within the nano gap, the already hybridized biomolecules hampers the entry of more biomolecules. So because of that, the biomolecules, how they are distributed within the nano gap, that consideration is taken into account and the sensitivity analysis has been done. Okay, so next is your effect of position. Please go to the next slide. Please go to the next slide. Effect of position of probe on sensitivity. This is another practical case. The degree of hybridization of probe and target molecule depends on the location of probes or receptors in the nano gap. The sensitivity in such cases is dependent on how the probe position influences the operation of the biosensor. This table shows the probe placement inside the nano gap for both CG TFET and HJ TFETs and lists different sensitivities in different cases. Sensitivity is more when the probe is placed near the tunneling junction. So the probe placement, now you see the total length of the nano gap is 25 nanometers. The table shows, and shaded area represents the biomolecule occupancy. Now biomolecule, depending on the shape, depending on how the biomolecules are occupied, the nano gap and the percentage of the surface area covered, the sensitivity for circular gate TFET and heterojunction TFET has been determined for different values of the dielectric constant of the biomolecules, and it has been calculated for different cases, and we can see at which position they are getting the highest value of sensitivity. So this is another practical case which is required to be incorporated. Without this, the simulation is not also complete. Now, what are the challenges? So what we have seen, the sensitivity is a factor which depends on the biomolecule dielectric constants, and depending on the negatively charged biomolecule, positively charged biomolecule, as well as steric hindrance and non-uniform hybridization, and the position of probe placement is also affecting the sensitivity. So what we have seen, but even though the circular gate TFET structure is showing the highest sensitivity, but all these we have considered in simulation, but we have some challenges for practical applications. So what are those challenges? Please go to the next slide. We'll see the challenges for the biosensor. So what are the challenges? Process-induced defects pose a serious threat to the operation of a FET. These defects become significant in TFETs because the tunnel junction is the most sensitive zone for the transistor. In case of a DM TFET, DM means dielectric modulated TFET, as a biosensor, the formation of a nano cavity in the gate dielectric is carried out by etching out a previously deposited gate dielectric material. This has immense possibility of creating damages to the gate oxide, examples being incomplete etching or damaged nitric oxide which is grown due to post etching. Okay, probe placement issues can significantly affect the sensitivities of a dielectric modulated TFET biosensor. The distribution of biomolecules in the gate embedded nanocavity is far from being ideal as considered in most cases in case of a theoretical analysis. So all these issues we have to consider. The formation of nanocavity issue should be etching out in a proper way. There should not be any damage to the device. So all these factors are the key factors while fabricating a biosensor. Okay, next the application of biosensor, I have just given an overview. Next I'll give an overview of TFET as light sensor. So see TFET as light sensor, how TFET can operate as a light sensor. All of you know photodetector. Go to the next slide. Sensors that convert a photon energy of light into electrical signal. Photodetector is a fundamental element of optical receiver. There are several photodetectors, photodiode, phototransistor, and photoresistors, etc. These are the simple photodetector we can use. Next, we can see photodetector requirement. What is the requirement of a photodetector? Good sensitivity at the desired wavelength, fast response time, high bandwidth, compatible physical dimensions, low noise, insensitive to temperature variations, long operating life, and cost effective. Obviously, everything is related to the cost. Until and unless low cost, it will not be effective. So cost is another factor. And obviously electrical parameters are also should be low noise, high bandwidth, fast response time. These are also major factors for photodetector requirement. Next is your wide photosensor. Need of photosensor. Go to the next slide. Optical sensors are increasing in impressive rate for being used in innumerable applications such as target tracking, chemical composition analysis, medical diagnosis and treatment, surveillance cameras, optical interconnects for inter-chip data communication, etc. Field effect transistors based sensors are of great interest because of its compatibility for integrated circuit. Obviously, field effect transistors are widely used because they have the compatibility for integrated circuits. Then classifications, and photodetectors are classified as, next slide, photodiode, PIN diode, avalanche photodiode, and MOSFET based photodetector. Please go to the next slide. Go to the next slide. What are the limitations? Low quantum efficiency. What is quantum efficiency? Quantum efficiency means how the photons are converted in terms of electrons. That is the measurement. Quantum efficiency measures how efficiently your electrons are converted from the photons. And effect of noise is low sensitivity, speed limitation of MOSFET based optical sensors due to its sub-threshold swing limit of 60 millivolt per decade. So these are the limitations of this photodetector. So in order to overcome those limitations, we will find a emerging device. So we will consider TFET based photosensor, more aggressive miniaturization. Next slide. Is possible in TFET due to its BT-BT current conduction mechanism, unlike thermionic emission of MOSFET. This work studies the TFET-based near-infrared optical sensor using a photosensitive photosensitive gate. It comprises of a photon absorbing N-type silicon gate along with a TFET structure. Silicon germanium heterostructure emerges due to N-type germanium pocket between the source and the channel junction. Already I have shown you the optically gated structure where you are using a germanium pocket. Why you are using germanium pocket? Because in order to increase the tunneling, or lateral as well as vertical tunneling, you can increase by adding a germanium pocket between the source and the channel junction. This allows a tunneling perpendicular to the gate stack, giving high on-state current. Now, here the next slide, figure 29. Figure 29 shows the N-type silicon gate-based TFET. Here the structure is shown. The drain is N plus gate is here gate is N-type silicon gate, where incident photon flux is shown in the figure. So this structure is acting as a N-type silicon gated based TFET. Next slide. What is the working principle of light sensor? That is a very important. The moderately doped N-type silicon gate absorbs incoming photon flux. Under the elimination state, for optical generation takes place, causing excess electron-hole pair generation. Those electrons having energy greater than the band gap of silicon will move from the valence band to the conduction band of the gate region, leading to the phenomenon called photogeneration. When positive gate voltage is applied, gate to source voltage is applied, the photogenerated electrons will attract towards the gate electrode, while the holes, photogenerated electrons will be attracted towards which side? Gate electrode side, while the holes will accumulate near the gate oxide interface. This separation of charge disturbs the equilibrium condition prevailing in the gate region. This results in the uncoupling of electron quasi-Fermi level and hole quasi-Fermi level, giving a net photovoltage across it. The net photovoltage VOP acts as an additional voltage to the VGS and lowers the gate voltage required to turn on the device, thereby increasing the BT current of the device. So this VOP generation is explained here. Net photovoltage is generated, and this photovoltage is acting as an additional voltage to the gate to source voltage, and which is acting in the opposite direction as that of the gate to source voltage. Now we can see the next slide. We can see the next slide. Go to the next slide. The structure, figure 30, figure A shows the schematic of proposed optically gated structure, and figure B shows the energy band diagram taken along the cut line AA dash, which is marked. AA dash cut line is marked in the figure A. So along that AA dash direction, the energy band diagram is taken, and energy band diagram EFP, the location of EFP, that is a quasi-Fermi level for hole, and EFN, that is a quasi-Fermi level for electrons, are shown in the figure, and how they are splitted. That diagram is shown under elimination state, figure B. And figure C, 30C, shows the corresponding energy band diagram under dark condition. Under dark condition, you can see the overlapping of Fermi energy level of electron and hole are shown in the figure. So this is the dark state and this is the illumination state. So at wavelength 0.7 micrometer, the graph is plotted for considering the wavelength at 0.7 micrometer. So observation, what we can observe? Ticket simulation view, you can observe, you can see under energy band diagram, under illumination and dark condition, an optical generation rate along the position from the monochromatic source, it is shown, and the operation of TFET, optical generation rate, is found to be has a very good generation rate. So that is why 4 into 10 to the power 25 per centimeter cube per second optical generation rate. So this rate is quite acceptable. So this device can be easily used as light sensor. And this paper is published in IEEE Sensors Journal in the year 2020 only, September 2020. So you can see the operation of TFET as the next slide. The graph 33 shows the transfer characteristic of proposed device, showing different drain current for various wavelengths. Now what we can observe here, with the increase of wavelength, our drain current is reducing. Now why drain current is reducing with the increase of wavelength? Because if energy is increasing, then our frequency, because we know that photon is the packet of energy, E is equal to H into nu. Frequency increases with the drain current. So if frequency increasing, the wavelength is reducing. In order to keep the velocity constant, the wavelength is reducing. If wavelength is reducing, then our current is also increasing, because my frequency is increasing, and due to the increased energy, more electrons are available, and then due to that, the drain current is increasing. And spectral sensitivity is also shown in the figure 34. Spectral sensitivity is maximum around 0.5 gate voltage, and threshold voltage and on current at with respect to next slide 35. I'll complete within 5 to 10 minutes. Okay. Threshold voltage and on current is also plotted at illumination wavelength lambda. So we can see the performance of this near infrared optical sensing device is measured in terms of spectral sensitivity, which is determined by the increase in drain current with the decrease in illumination wavelength from lambda 2 to lambda 1. So threshold voltage, how threshold voltage is changing, and how the on current is also changing with the illumination wavelength. The figure is showing that. So the sensitivity, how we are measuring the sensitivity, the formula is given. Sensitivity ID at lambda 1 minus ID at lambda 2 by ID lambda 2. So the sensitivity we can easily measure. The proposed device also poses a higher illumination current, lower threshold voltage, and higher ion-off ratio under the incident radiation, making it a suitable device for low power operation. So this is a TFET based infrared sensors, can be a promising candidate for replacing MOSFETs in near future. Now next is the, I am in a hurry, time is less. So application of TFET in RF energy harvesting. Just I will show you how TFETs can be used in RF energy harvesting. Just introduction, radio frequency powered energy harvesting systems have explored new perspectives in various scientific and clinical applications in health monitoring, biosignal acquisition, battery-less data transceivers, and RF rectifier with high sensitivity, high power conversion efficiency is critical to enable the utilization of the ambient RF signal power. So the power consumption of these systems ranges from few microwatts to milliwatts. That is why this radio frequency systems are utilizing new devices. How you can see the block diagram of RF powered system. So RF powered energy harvesting system is shown. So energy harvesting power management is consisting of 4 blocks. One is the impedance matching, another is rectifier, another voltage booster, and voltage regulator. While impedance matching RF power is coming, so in order to get a maximum power transfer, we are considering a impedance matching network. Then rectifier is required to convert RF power into DC, and voltage booster circuit is required because the voltage level is very low. So that is why voltage booster circuit is used. Now in energy harvesting application, in rectifier, RF to DC converter rectifier, the diodes can be replaced by the TFETs. So that application you can see. So I am not saying in detail, just brief. There are various types of
already rectifier designs are available, but these designs suffer from the efficiency loss induced by large threshold voltage, large turn-on voltage. Hence, the maximum power conversion efficiency is not obtained, which is found to be very small. So, in order to increase the maximum power conversion efficiency to a maximum level, we want to reduce various losses. So that reduction is possible only when if we use a emerging device. So the rectifier operation requires the RF signal voltage amplitude above the turn-on voltage of a transistor or a diode. In the subthreshold regime, a large on-state channel resistance due to the drive current reduction induces an increased voltage drop of the rectifier, which leads to a high resistive power loss and reduced output voltage. Therefore, a device with small turn-on voltage is preferred. So these factors, next slide, the key performance parameters. Next slide. Key performance parameter of RF rectifier are nothing but DC output power, DC output voltage, and power conversion efficiency. Now, power conversion efficiency, output power is twice of VAC minus V drop, where VAC is the RMS voltage of the input because it is a rectifier, and Pin is the RF input power, and V drop is a voltage drop across the rectifier circuit. Now, power conversion efficiency is what? Output power by the input power. Now, input power is nothing but P naught output plus the P losses. Losses due to leakage, reverse switching, redistribute, and resistive losses. Leakage is due to the transistor offstate leakage. Switching loss is due to the average capacitive switching loss. Next slide.
Hello, ma'am. Hello, 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 hello. Hello. मेरा अपना वॉइस क्या ओ अच्छा अच्छा मैडम इसलिए हमारा स्टोरी
Hello, participants. There are some issue, I think, with the um, speaker. She logged out because of the network issue. She will be joining back and will take questions from audience.
Hello? Hello? Can you hear?
Yes, ma'am. Continue. Continue.
Okay. So please, design of RF rectifier. Show the next slide. So here, the impedance matching network is shown in the figure. Equivalent circuit of RF rectifier. Okay. So next is I will show you different topologies of the rectifier, where you can use TFET. Next, this is the equivalent circuit of RF rectifier. So theory part I am leaving. Just go to the next circuit, 38, slide number 78. So various topologies. One topology is two transistor topology of rectifier, where we can use one N-type and one P-type TFET. Okay, and operation only you can. It is already available. And next slide. Slide number 80. Another is a 4T topology. There is a 4 transistor topology where we can use two N-type TFET and two P-type TFET. And next slide. Another is 4NT topology where there are two N-type TFETs. M1 and M3 are the two N-type TFETs, and two P-type TFETs are replaced by diode connected TFETs. Because why? To mitigate the P-TFET suffers from degraded subthreshold swing. So in order to mitigate that, they are replaced by diode connected N TFETs. Okay. Next, so these are the various last. Go to the slide number. Next slide. CG TFET in P and N mode. The graph is shown for P TFET operation, CG TFET, and N TFET. P TFET operation is shown by red color, and N TFET operation is shown by blue. N TFET operation is shown by black color. So like that, we can use N TFET and P TFET, circular gate TFET as both. Next, RF rectifier waveforms. So the wave voltage waveform is shown, and the input as well as the current. Current for transistor M1 is plotted for both HJ TFET as well as the CG TFET. It has been found that for a CG TFET, current is less, but for HJ TFET, the rectifier operation current, when you measure the current for M1 transistor, the current is found to be more, but in the reverse direction. Okay, same as that of the input, because you are operating it as a rectifier. And these for below 6 volt amplitude, the rectifiers cannot be operated because of the threshold voltage limitation of TFET. So still research is going on as RF rectifier operation, and we can see, go to the slide number 87. We can see the different comparison of different topologies of RF rectifier output. Output power, DC output is compared for 2T, 4T, and 4N topologies, and it has been found that 2T topology will give you the highest output voltage. And next slide. In the next slide, the power conversion efficiency, output voltage, threshold voltage, ion current, subthreshold swing of two types of TFET is shown, and their values are compared. And we can use those two TFET in RF application as RF rectifier application, and we can get a high efficiency of 80%, near about 80% efficiency can be obtained, and power conversion efficiency is high. High sensitivity RF rectifier designs is possible. Reduced terminal voltage, drive current improvement, steep subthreshold swing, high frequency characteristics, desert high frequency characteristics are the superior performance of TFET structure. So in near future, we can replace our TFET, we can replace MOSFET or CMOS by TFET for biosensor as well as light sensor as well as RF energy harvesting applications. These are the various next references used. Most of the structures are from my paper or which are already published, and references, some references also I have used. And last is acknowledgement. Now I want to express my sincere gratitude to MNIT TechUp3 for organizing online workshop on emerging CMOS technologies and beyond, trends and challenges. Also, I want to thank coordinators Dr. Rajesh Chaha, Dr. Bharat Chaudhary, and convener Dr. Chitrakant Sahu, and special thanks to Director Sir Professor Uday Kumar Yaragatti. Okay, thank you, sir, for inviting me.
and I am very happy. And whether my presentation is helpful to participants or not, please inform me. Or if you have any doubt, please you can ask.
Ma'am, can you see the questions in the chat box? Hello?
Chat box.
In the chat box, questions are there. Are it visible for you? You can read the question. Okay, if it is not visible, I can read it also.
Hello?
Yes, ma'am. Questions are visible in the chat box.
Chat box. Okay, I am trying to see.
Otherwise, I can read it. No issue.
Okay, okay, I'm trying to open.
Actually, the first question is what is the difference between?
I got one question. Will FinFET sensor work better than TFET sensors?
Ma'am, go to the first question. It is above.
Which one is the first question?
What is the difference between local and non-local VTBT, and at what conditions?
I have two questions.
Okay, but
Hello?
yes, ma'am, you continue first. Later on.
You just tell me what is the first question.
Yes, ma'am. You first you tell your means whatever the questions with you, you tell. Then after that,
Will FinFET first? I'm question one question I'm getting. Will FinFET sensors work better than TFET sensors? This is depending on the situation. You have to check whether the your proposed structure has good characteristics. You say you have proposed a FinFET structure and you have proposed a TFET structure. Both you have to compare whether if your FinFET structure is very good, means it has very good electrical characteristics, then it may happen that your FinFET may give you better option, better. But most of the cases you will find TFET is found to be better than FinFET, because TFET operating principle is based on band-to-band tunneling, which is free from the subthreshold swing limit, but FinFET has high subthreshold swing values. You cannot reduce the subthreshold swing in FinFET. So most of the cases you will find the TFET sensors, if you consider modified structures, obviously, all the electrical characteristics should be according to ITRS requirement, then your FinFET structure will be degraded than the TFET. Okay, next question. Hello?
any other question with you, ma'am?
I have seen only one question and one answer.
Okay, the next question is, ma'am, what is the difference between local and non-local VTBT, and at what conditions do you apply?
Non-local conditions actually is the basic condition will apply. Non-local means when the electric field at this point are very high and there is direct indirect tunneling, both may possible. In this case we'll apply the non-local tunneling mechanism.
And local tunneling, madam?
Local tunneling we are not applying. We are applying either non-local models or we are applying either Shank models.
Okay. Ma'am, next question is why on-kind reduces when germanium mole fraction is greater than 0.3?
Why? Reduces. Why current reduces when germanium mole fraction is less than
greater than 0.3.
3.
Yes,
0.3.
3.
Yeah. It is reducing because of the fact that whenever you get the energy band diagram, the band bending is very important. It is not that whenever you increase the mole fraction of germanium, we are reaching more towards the low band gap material. Along with the low band gap material, my delta phi factor, that factor which is available in tunneling probability, delta phi is another deciding factor for increase of tunneling probability. Now, if delta phi you can modulate, we can see the band diagram and we can observe the band bending. Depending on the band bending, my delta phi is depending. So whenever we increase the mole fraction above 0.3, then we'll find that my band bending is such that my delta phi is not allowing, is decreasing. Therefore, due to the band bending effect, my current is the current of TFET is decreasing with the increase of mole fraction, even though the band gap is moving towards the low band gap material. Okay.
Yes, ma'am. Then next question is how photon flux incident on gate in the simulation tool. How photon flux
Simulation
incident
today,
on gate in the simulation.
that is available. You can see optical ticket structure, optically devices are how it is given. It is already given in the manual that people can see.
Okay. Then next question is in case of optical sensor, if you
Yeah.
target to sense specific wavelength, then it is possible to
In case of optical
incorporate
sensors,
some metal oxide sensing material to silicon in tunnel phase.
question
Ma'am,
is not clear. Please
I'm
read.
repeating the question. In case of optical sensor, if we target to sense specific wavelength, is it possible to incorporate some metal oxide sensing material to silicon in tunnel phase?
Metal oxides.
Yes. Is it possible to incorporate some metal oxide sensing
Where?
material to silicon in tunnel phase?
Yeah, that is possible. Anything you can do. But where metal oxides they want to incorporate.
Yes,
Where?
yes, they want to incorporate. One student from Polash Pukon, he asked this question.
Yeah, metal oxides you can incorporate, but you without before using it as a light sensor, what you have to do, you have to check its electrical properties, whether it is obeying all the properties according to the ITRS requirement. Then only you can do that. Otherwise, and another thing, that is interface property. You cannot use any oxide, na? You have to consider interface property as well as all the electrical properties, whether all the electrical properties of the particular device are according to the ITRS requirement or not.
Okay. Ma'am, next question from Nagendra. Nagendra is
Yeah.
asking that what is the alternate method to reduce the ambipolar behavior of TFET other than your gate underlap drain method? Gate underlap drain method.
There are various
Any other alternative method?
there are various ways. Gate underlap is one of that way. Another way is that at the drain side, that I have already shown you, in the drain side I have raised the buried oxide. Buried oxide can be raised in the drain side only. That is another option I have already shown. But you can another ambipolarity you can also reduce by using some applying some lightly doped drain also. That also I have not done any, but you can check. If you want to do, you can add one lightly doped drain near the drain channel junction, and you can see the effect also.
Okay.
And stacked layers of various semiconductors can also be used.
Okay. Ma'am, next question is, can we include vertical tunneling in nanowire gate all around TFET?
Vertical tunneling, yeah. No, vertical tunneling.
Nanowire gate all around TFET.
Gate all around where you need the vertical tunneling. Yes, it is possible, because vertical tunneling means tunneling should be perpendicular to the interface of gate oxide and silicon. You have to put a layer. You have to put an extra pocket in such a manner that the vertical tunneling may take place.
Ma'am, next question from Santosh Kumar. What are the recent research area we need to focus on? Means recent research area we need to focus.
Recent research area. One of the major recent research area is a biosensor application, light sensor applications. I have already shown, and many other research areas are also there. Many types of sensors are available. Only I have used light and gates, that biosensor. Others, many types of sensors are there. Say gas sensors, and you can use some Monte Carlo simulations there. So many things are available.
Ma'am, next question from Reddy. Which structure is more suitable for biosensor among planar 2D or nano? Which structure is more suitable for biosensor among
Which
your structure? Yes, planar 2D structure or nanowire gate all around structure?
Nanowire gate all around structure, if the characteristics are good, then it will be more useful, because in the nanowire structures, the cylindrical structure, nanowire, so it will be more suitable, I think so. But I have to check the properties now. Until only if you ask the device, I can't say, because we have to check other properties also, that is important. Whenever you can say a device is very novel,
Then you have to check all the properties: high frequency characteristic, low frequency characteristic, noise, electrical parameters, then digital on current, off current ratio, then your subthreshold swing, everything should be considered. Otherwise, you just by name of the device, you can't say.
Ma'am, one student directly want to ask question.
Okay.
Nagendra, you can ask the question now. If you have any other question.
Hello.
Hello.
Yes.
Tell me.
Good afternoon, ma'am.
Yeah. Good afternoon.
Ma'am, can we use AC characteristics of a TFET as a sensitivity parameter for the biosensor?
AC characteristics.
Yes, ma'am. Like frequency and capacitance.
Yeah, capacitance variation also can be sensed. That is also a factor. Capacitance means how capacitive effect, because whenever you change the dielectric constant in the gate, because by your use you are replacing biomolecules, na? So biomolecules
Yes,
having
ma'am.
different dielectric constants. So instead of measuring current in terms of capacitance, also you can do that. Can also be a very good work.
Okay, ma'am. Thank you. Ma'am, one more question.
Yeah.
Madam, we are while developing the different structures, we are using unsymmetric for a source as well as drain. So actually,
Yes.
is there any effect on the sensitivity if you use a different, measurement for the source, drain, and channel?
No, you are using what? I did not understand.
Actually, for any kind of sensor, we are using different unsymmetric structures, ma'am. Like source, we having length 50 nanometers. Somewhere drain is having 25 nanometers.
Asymmetric length you were saying, or asymmetric
Yes,
doping.
ma'am.
What is asymmetric? What is that?
Asymmetric length, ma'am.
Length. Okay, this is not a problem. Length is not an issue in the drain side. It's outside
Okay.
also. Beyond the tunnel junction, whenever if you increase the length, that length has no effect on the current.
Okay.
Current is only
Okay.
affected by tunnel source junction, channel, and the drain source junction up to the depletion layer. After that, you increase it, no problem. But if you increase, if you make it very big, then why you are making nanometer devices, na? So keep it
Yes,
at
ma'am.
least nanometer total device length. Should not be beyond that.
Okay, ma'am. Thank you, ma'am.
Okay, all questions are over,
Yes, ma'am. All the questions are over. Ma'am,
and all
thank
are
you very much.
happy.
Hello.
All participants are satisfied.
Yes,
I
yes.
think
They are saying that all the information are very helpful for their research work.
very good, because research, they can do research, because TFET is still under research. All of you, all people can do research, those who are interested in device. Okay. So
Okay, ma'am,
I
thank you. I
finally
want to thank
thank
you.
all of you. And you have faced problem due to my connection, network connection, and you have wasted your time also. For that also I want to thank, and I will please pardon me also what I can do, because here connection is like that only. We can
Yes, ma'am.
Google
We
Meet,
have also.
otherwise WebEx, it is always like that.
Okay,
Okay.
ma'am. Thank you, ma'am. Thank you, ma'am.
Okay.
Thank you.
Thank you.
And participants,
Okay.
the next session will start at 2
I
p.m.
can means I can
Yes,
remove,
ma'am.
na?
Yes, ma'am. You can
Okay.
leave the meeting, ma'am.
Okay, I can leave.
Participants, remaining the participants, you can join to the link at 2 p.m. Okay, we have the next lecture on uh, circuit applications of the tunnel FET. Okay, with the next lecture on circuit applications of tunnel FET, you can join the link at sharp 2 p.m. Okay, thank you. इतना दर्शन बाद आ जाएगा वो